Hello guys. So in the last lectures we have started with the fifth unit second chapter, that is column. Till now we have covered Euler's formula. Okay, the assumptions to derive this Euler's formula. We have also solved different sums related to Euler's formula. That is for long column. We have solved different sums on long column. Now today we will start the Rankine's theory, which can be applied for long column also and also for short column. Mostly Rankine's theory is applied for medium length column and short column. Okay, in the Euler's theory, only long columns are analyzed to calculate the critical load, to calculate the stresses induced in the long column. But in Rankine's theory, okay, Rankines have considered compressive stress also and buckling load also. Rather than in Euler's theory, they have considered only Euler's load only. Okay, so let's see how the Rankine's formula has been derived. Okay, so the critical load can be determined by using this formula. Okay, 1 by P is equal to 1 by PC plus 1 by PE, where P is Rankine crippling load. Okay, the load at which the short column will crush. Okay, so the short column will fail. Okay, so the failure of the short column is nothing but by crushing. Okay, as in long column the failure of the column is by buckling. Getting my point? So P is Rankine's crippling load, PC is ultimate load. Okay, and it can be determined by using ultimate stress into area, cross sectional area. PE is the Euler's load. Okay, so if you do some inverse calculation like this, okay, so P on P and PC by taking denominator equating denominator, okay, and doing this calculation. So PC we can write for PC sigma C into A. Okay, sigma C is the compressive stress, okay, that is applied on the short column. Okay, A is cross sectional area. P, for P we can write pi square EI upon LE square. Okay, pi square EI upon LE square. So by taking some constant value like sigma C, pi square and E, sigma C, pi square and E common outside and taking in bracket, okay, we can write A into LE will go to the numerator. Okay, so A into LE square upon I. For I, moment of inertia, we can write AK square. So A will get cancelled. So LE square by K square will be there. Okay, like this. Okay, for this sigma C by pi square E, we can write alpha, where alpha is called as Rankine's constant. Okay, so the Rankine constant will depend upon material property, because we know that sigma C is nothing but ultimate stress that is acting on a column. Okay, and ultimate stress will be different for different material, and also the modulus of elasticity also different for different material. Because of that, alpha will be different for different material. Okay, that is alpha is Rankine's constant. So it is sigma C by pi square E. So the formula for Rankine's crippling load, that is P is equal to sigma C into A upon 1 plus alpha LE by K bracket square, where LE is the equivalent length. Okay, it will be different for different end conditions of the column, like, right? So the different end conditions are both ends are hinged, one end is fixed, other end is hinged. Okay, one end is fixed, other end is free, right? Getting my point? So likewise we have determined the equivalent lengths that already we have studied in the last lectures. Okay, when there is a short column is very small, in that case the crippling load is equal to the compressive load only. When for long column, this crippling load will be equal to the Euler's load. Okay, getting my point? So we just need to remember this formula, and always remember that the calculation will be a bit difficult if you do in one step only in your calci. So for that you need to calculate the numerator separately and denominator separately, and after that you will get the crippling load. Okay, so use the calci very well. Okay, because of that you will get the proper and accurate answer. Okay, so don't mess up with the calci. Okay, by doing calculation in single step only. Okay, so determine numerator first, then denominator. Okay, now we'll see a question. Okay, a 3.2 meter long fixed end hollow has internal and external diameter as 60 and 80 mm. Determine Rankine's load with the crushing stress 500 MPa and alpha 1 by 1600. Okay, so the crushing stress is nothing but sigma c, alpha Rankine's constant, inner diameter and outer diameter is given, and the length also given. Okay, what we need to determine? Rankine's load. Okay, so just write the given data: sigma c, length, inner diameter, outer diameter. First we will determine LE by K separately, because we need to determine this ratio to calculate the crippling load. So first we will determine this ratio. For that we need to determine moment of inertia and then radius of gyration, that is K. Okay, so by moment of inertia is equal to AK square. Okay, moment of inertia is pi by 64 dO raised to 4 minus di raised to 4 upon pi by 4 dO square minus di square. Okay, pi will get cancelled, so it will be like this, and you will get the K value as 25 mm. Okay, just do the calculation, you will get the same value. Okay, find out LE by K. Now here you can see in the question it is long fixed end hollow internal and external tube is there. Okay, so fixed end, that means both ends are fixed. So both ends are fixed, we know that the equivalent length will be L by 2. Equivalent length will be L by 2. Okay, that is 1600. Okay, so we'll find out the slenderness ratio, that is LE by K. So the slenderness ratio is 64. Okay, now just put the values. Okay, in this equation you will get our critical Rankine's critical load 308.864 kilonewton. Right. So in this formula you need to determine first numerator, then denominator, and then take ratio. Okay, that will be easy to calculate the critical load. Right. Now we will see some difficult questions to determine or to design the short column. To design the short column, that means we need to determine inner and outer diameter or dimensions. Okay, by using the critical load. Okay, now we'll see the next question. So 4 meter long cast iron hollow, both ends are firmly fixed supports and axle load 400 kilonewton. Okay, the inside diameter is 0.6 times the external diameter. Okay, inside diameter is 0.6 times the external diameter. Determine section of the column where factor of safety is 5, maximum compressive stress is 560 MPa, and alpha is 1 by 1600. Okay, right. So factor of safety is given, maximum compressive stress is given, alpha, that is Rankine's constant, is also given. Okay, the load is also given, that is 400 kilonewton. Okay, and both ends are fixed. The length is also given, 4 meter. Okay, so firstly by using factor of safety we will calculate the safe compressive stress that the buckling the short column can take. Okay, the safe compressive stress, that will be factor of safety is equal to maximum stress upon compressive stress. Okay, so 560 by 5, that will be safe compressive stress. Okay, as both ends are fixed, because of that equivalent length will be equal to L by 2, that is 4 by 2, that is 2 meter. Okay, as both ends are fixed, so it will be L by 2, that will be 2 meter. Okay, inner diameter is equal to 0.6 times outer diameter as it is given. Now we will determine radius of gyration in terms of outer diameter. Okay, so I is equal to AK square. For I, we know that the moment of inertia will be pi by 64 dO raised to 4 minus di raised to 4, and area will be pi by 4 dO square minus di square into K square. So pi will get cancelled. The calculation will be like this: For inner diameter, put the value in terms of outer diameter, that is 0.6 times outer diameter. Okay, so it will be like this. Do the calculation. 1 by 16. Take this outside. So do square will get cancelled. So do raised to 4 upon do square. If you take this common, okay, do raised to 4 common outside, do square common outside, and just do the calculation of these numbers, okay, you will get the k square is equal to 0.085 do square. 0.085 do square. Okay. Now, as we know the value of crippling load, we know the value of sigma c, but we don't know the dimensions, that is k and a. Just put the values. Okay, as alpha is also given and length is also equivalent length also we know. Just the given values. Okay, P 400 kilonewton, that is 410 to the power 3. Sigma c, that is shape working stress 112. Area pi by 4. Do square minus di square, so it will be 0.64 do square. Okay, it has some calculation. Okay, 1 plus alpha 1 by 600. Okay, LE 2000 square. Okay, equivalent length is 2 meters, so it will be 2000 its square upon k square is 0.085 do square. Okay, just put here the values. Okay, carefully do the calculations. Okay, you need to do stepwise calculation, don't hurry. Okay, just do calculation carefully. Okay, so it will take multiplication on this side. Okay, so like this. Okay, take denominator to the numerator. Okay, so it will be do raised to square goes to the numerator, it will become do raised to 4. Okay, now take this term on left side, multiply with the 410 to the power 3, you will get this value, and take this side on, okay, this value on left side, so you will have the quadratic equation in terms of do square. Okay, in terms of do square. Okay, quadratic equation in terms of do square. So first find out do square and then find do. Okay, so do will be 123.7 and by multiplying 0.6 to this value we will get inner diameter 74.22 Okay, carefully do this calculation. Okay, you can do this calculation in calc also. Okay, by using quadratic equation in terms of do square. So first find out do square and then take a root of do square, you will get do, and multiply it with the 0.6, you will get di as it is given in the question. Okay, right? So far we have covered torsion, and in the next lecture series we have covered column. Okay, in the columns we have studied different end conditions of the column, what is meant by column, what are the different types of the column like short column, long column, what are the different equilibrium conditions, right? What are different end conditions of the column, like both ends fixed, one end is hinged, other end is fixed, both ends hinged, one end is fixed, other end is free. After that we have solved different questions on the Euler's theory. Okay, where it is used. Okay, where Euler's theory, for which type of column it is used. After that, for short column we have studied Rankine's theory. Okay, we have derived the formula for Rankine's crippling load, right? After that we have solved different questions on the short column also by using Rankine's critical load formula. Okay, so by that I can say that we have covered entire 5 unit. Okay, entire 5th unit. Okay, so we have finished 5th unit by both chapter torsion and column. Okay, thank you very much. In the next lecture series we will see 6th unit, that is principal stresses and strain. Thank you very much.